All right. So in this video, I'm just going to show my approach for the playground competition uh, for the month of June. So then here on the Kaggle website, so this is a tabular competition. Just to give you a little bit of background in terms of what the competition is and how the solution is being evaluated. So let's go over the overview page. So this is a tabular competition, so meaning that the data set that we're going to be analyzing here has rows and columns. There is a specific column that we are trying to predict in this case. So the data that is being used for this particular competition is a synthetic data set that it was generated from a pre-existing data set. So the original data set is shown here. So it's about fertilizer prediction. So then basically this is a data set that has information related to fertilizer. So we have different attributes of, different conditions: temperature, humidity, moisture, soil type, crop type, nitrogen concentration, potassium, phosphorus, fertilizer name. So in this particular case, fertilizer name, it is the target variable that we're trying to predict. So this is the original data set that the Kaggle team used to generate a synthetic data set. So, and that is the data set that is being provided for the competition here. Okay. So pretty straightforward. There is not much to be said about the data. It has rows, it has columns, it's related to agriculture, and at the end of the day, we're trying to predict the fertilizer name, which, as you saw here, is a categorical variable. So we have different labels. Then if I remember correctly, there are 7 different labels here. So then when you think about this particular task, you can think of as a multi-class classification problem. Okay, so then we have a set of features, and then we're trying to predict 7 different labels. Okay, how the solutions are going to be evaluated is they're going to be evaluated using the mean average precision at 3. Okay, so this is a very, very common metric that is used to evaluate recommendation systems. So basically, what we are required to do is for each row in the test data set, we are expected to predict 3 labels. Okay, obviously the first label is going to be the one that is the most likely, then the second one, and then the third one. Okay, and the way how this metrics works is if the first label happens to be the true label, so then you get 1 point. If the second label, it is the true label, then you get half of a point. And if the third label happens to be the true label, then you get 1/3 of a point. And if none of the 3 predicted labels are the true labels, you get 0 points. Okay, so this is a very common metric that is used in recommendation systems. Okay, and then that is the metric that we will try to optimize here. In terms of how we are supposed to create the file for submission purposes, so then for each observation on the test data set, we are expected to predict 3 labels. Okay, and this was a month-long competition. And Kaggle has these competitions every single month, and most of the time there are tabular competitions in which Kagglers around the world, they if they want to get more familiar with different machine learning algorithms, so that will be the best way to start. If you want to practice and to polish your machine learning skills, that also will be a great competition to be part of. So then that's basically a quick overview of this episode. Again, the data that they provide is a synthetic data set that it was generated from this data set. And if you're wondering about how they generate the data set, typically, there is some sort of like a GAN model. So then that's a generative additive network model that they use for training the model. And once the model learns, some of the patterns that may be present on the data, it start generating synthetic data. Okay. Yeah, so then typically on these type of competitions you have up to 5 submissions per day. All right, so now let's jump into my notebook that I use, that I publish. So anytime that there is one of these type of competitions, so then I create a notebook in which I, share some initial findings, some initial models, and then I use that as a starting point for more complicated or for more complex solutions for the competition. So as usual on these notebooks, I start by loading all the libraries that I will be using. Then here I just, I use pandas just to read the data, nothing complicated here. I always like to print the first 5 observations just to get an idea about the data. So as you can see here, we have, all of these features, and then this one right here is the one that we will predict. And I do the same for the test data set. Nothing interesting to say to learn out of, just printing the heads and tails of the data set. And then I just jump into exploring the data. So then the very first thing that I always do is just take a look at the target variable, which in this case is fertilizer name, and it's a categorical variable. So then anytime that you're working with categorical variables, so then you would like to get an idea about the frequency distribution of that variable. So then that's what we see here. So we see the 7 different labels. So then the proportions more or less are, some number between 12 and 15%. So there is no much unbalancedness in the data, so then it's pretty balanced. Then after that, I start looking into duplicate rows. I start looking for observations that they may appear on the train or test data set. And if you're wondering about why am I doing that, I've been competing in these playground competitions for a while, for a few years by now. So then those are kind of the sanity checks that you always want to keep an eye on, because again, given the nature of how the data is being generated, sometimes the network or the model that the Kaggle team is using to generate this data may, generate duplicate information, and maybe there is some sort of like, observations that they appear on the test data set and on the train data set, and then maybe you can take advantage of that scenario just to improve your overall score. So I always do that, check for duplicates, check for potential observations that may appear on the train and test data set at the same time. So there was none of those scenarios in this particular data set. Then I start looking for missing values, no missing values at all. And then after that, I jump right into, creating charts just to get a better idea about the data. And the reason why you start creating charts out of the data is just to see if there is some sort of relationship that you can exploit for modeling purposes. This particular data set, I here on my notebook, I have only a few charts, but I create other charts. All of them, they look like this. So when you look at this, and in this particular case, I'm just comparing the temperature for the different fertilizers, and here I'm comparing the humidity for the different fertilizers. Everything looks random. Okay, so then when you see side-by-side box plots and they look very, very similar, so then that means that there is pretty much no relationship between those two variables. Okay, and that is the case for pretty much all of the variables. So that right there tells us, the data set is very noisy, and that's something that Kagglers were able to identify pretty much on day number 2 of the competition, that the data is very, very noisy, and there is very, very little signal that you can exploit for predictive purposes. So there is not much to learn from the exploration, because again, I'm just showing 6 different charts, but I create other charts and pretty much it was the same thing, the same takeaway message. Noisy, a lot of noise, not much to be learned. Then after that, I just jump into the modeling. And typically when I start modeling, at least at the beginning, I don't do anything fancy. Basically what I just focus on is just, let's use the raw data and let's just run a very simple cross-validation experiment just to see how the models are processing the data and how good the models can be at predicting the target variable. So I typically start with traditional algorithms, meaning that I typically start with either LightGBM, XGBoost, CatBoost, Random Forest, you name it. So all of those tree-based models, so then I always use them at the beginning. Why? I mean, there are very well-known algorithms. They don't require much pre-processing, and then they tend to work really well on tabular data sets. So I start by defining my input using a very standard notation X. I use Y for the target. In this case, again, the target variable happens to be a label, so then we need to map that labels into numbers. So I'm using label encoder from scikit-learn. And whatever we do on the train data set, we need to replicate that on the test data set. And then here I define my cross-validation and strategy. So I'm using a 10-fold cross-validation. And then I start with CatBoost. CatBoost, again, anytime that I'm working with a data set that happens to have categorical variables, the first algorithm that comes to mind is CatBoost. Why? Because CatBoost is the boosted tree algorithm that it was developed to process categorical data. Okay, so here I just define the hyperparameters. So then in this particular competition, again, you can do some hyperparameter tuning, but because of the size of the data set, which is showing somewhere here, if I remember correctly. So it's a medium, it's not that a huge data set, but it's a medium sized data set, okay? So pretty much 750,000 rows. So doing hyperparameter tuning may be a little bit overwhelming if you don't have the right computing environment. So I did some hyperparameter tuning, but I didn't spend much time into it. Okay, so then here is my hyperparameters that I use just as a starting point. Here I define which columns are the categorical features. That's something that you need to pass into CatBoost. And then after that, I start going over my traditional cross-validation experiment using a for loop. And then at each time, we are computing that mean average precision at 3. So then again, we're doing this, we're splitting the data into 10 groups. So we're grabbing 9 of those groups for training purposes. We're leaving one group out of the training process. That group that is left out, so that's the one that we're going to use for evaluation purposes. So we use these 9 groups, we build the data here, and then we predict on the fold or on the group that is left out. And then we predict the 3 labels for each of those observations, and then we compute the mean average precision at 3. And I print that score for each fold. So then those are the scores that we get on each fold, and then this is the overall average score. So then this number is just the average of these 10 scores. And then basically I also ran another simple experiment now using XGBoost, pretty much same thing. So then just run your cross validation, print the score at each fold, and then print the overall score. So here we got slightly better results. So then we went from this number 0.2746 to 0.2819. So then keep in mind that when it comes to the mean average precision, the higher that value is, the better. Okay. And then after that, I also trained a LightGBM model. So here are the hyperparameters that I use, and again the standard cross-validation experiment. Then I print all the scores for each of the fold, and this is the overall score. Okay. So this is just a starter notebook. So then I always publish one of these just to get just to get familiar with the data, to get familiar with the metric that we're trying to optimize, and just to get an idea of what models are working on this data set and what models are not working on the data set. Okay. All right. So then after that, then you need to, especially for these kind of competitions, you need to run a bunch of different experiments. Okay. So before I jump into that, let me go back to the Kaggle site. So here you can see my submission. So then I ended up with submitting 98 solutions. Okay. So, and then you can see the scores here of every submission. So then you always get, at the end of the competition, they show the private score and the public score. So for those who are not familiar with Kaggle and how your solution is being scored, typically, whenever you start submitting, once you start submitting answers to the competition, you're gonna get a score. Okay. And then typically that score is going to be what they call the public score, and that is based only on 20% of the data. And that's supposed to give you some sort of idea in terms of, whether your model or your framework is working or not. Okay. However, having a great public score is not always going to translate into having a great private score, because what happened is, like, sometimes you ended up overfitting the public data set, and then you may end up with a very high score on the public, but then once the private gets released, then maybe you don't have a great score. So in my case, so you can see that on the public leaderboard, I was on 173. So I was ranked 173 out of 2,650 different teams. But again, what it matters at the end is how well your solution does on the private leaderboard. And on the private, I ended up on the 21st position. Okay, again, 21st out of 2,650 teams. Okay. And then here, you can see all of my scores, and then how, I start at 0.332 pretty much, and then I start making improvements week after week. I start making more improvements, and then eventually this was my best solution. Okay, so now what I'm going to show you is how do I get to these numbers? All right. So as you can see here, I use VS Code as the software to write code and to run my different machine learning experiments. So it's pretty easy to use. I have the notebook extension installed, so then I like to use notebooks, especially when you're just experimenting with different models, different ideas. So in my opinion, notebooks are the best way to do that. Okay, here, as you can see on the left, these are all the different experiments that I ran. Okay, so before jumping into what is my final solution, let me quickly show you one more thing. So here I have my what is it here? Yes, so then this is my write-up. So then typically, again, at the end of each Kaggle competition, so Kagglers, they like to share their approach. So then, and that's why this is a great platform. And I always, when people ask me about Kaggle, I always tell the same story. To me, is the best thing when it comes to data science, machine learning, and AI. So because you are learning from each other, and the community is nice enough in the sense that at the end of each competition, pretty much everyone starts sharing their secrets in some sense. So yeah, in my case, So then here I just quickly summarize, the number of models that I trained on the data. So these are the different algorithms that I consider. So CatBoost, LightGBM using Ghost as the booster, XGBoost, logistic regression, multinomial naive Bayes, and gradient boosted trees learner. I also spent some time playing with TensorFlow and building neural networks, but I couldn't get it to a very competitive level, so then I exclude that from the list of models. So all of those models were trained over a tenfold cross-validation strategy. Right from I think it was halfway through week 1, Kagglers identified that doing like some sort of like a weighted average combination of your different models were not improving the overall performance of an individual model. So, and that's something that I also experienced. So what it was identified right on week 1 is that stacking was the technique that it was improving the overall performance of any individual model. So then basically the idea behind stacking, so if you're not familiar with that, is the following. So the stacking overview. So basically what you need to do when it comes to stacking, so then you need to have different models. So then let's say this, you could call this model 1, then you can have here model 2, maybe here you have model 3 or model 5, whatever, right? Just for illustration purposes. So what happened is like you need to use the predictions from different models, and you will use that as inputs into another model. So you use the prediction from that model, from this model, from this model into another model that typically is called the stacker, or also in the machine learning community is referred to as, so let me write this correctly. So stacker or meta learner. Okay, so you use the predictions from 3, 4, 5, whatever the case may be, of different models, those predictions as inputs into another model. That specific framework is called stacker or stacking. Okay, so I think before the end of week 1, so on this particular competition, Kagglers identified that stacking was the approach to consider in order to improve your score. Okay, so in my case, or at least based on what it was being shared through the different public notebooks, so then everybody, or not everyone, but then most of the top scoring notebooks, they were going with logistic regression as the meta learner. Okay, so I also built a few different stackers using logistic regression, but I wasn't getting consistency in terms of my local CB score and the public leader score. So in some cases, when my local CB score was improving, the public leaderboard was not improving. So then at that point, I was like, okay, logistic regression is not that stable, so let me try something else. So then that's when I decided to use linear discriminant analysis as the meta learner. So if you are not familiar with linear discriminant analysis, it's just an statistical technique that you can use it for classification purposes. Okay, it's pretty simple to use. And Scikit-learn has a very simple implementation of linear discriminant analysis that you can rely on. Okay, when I started using linear discriminant analysis as my final estimator, that's when I start having consistency between my local CB score and the public leaderboard score. And I also tried Gaussian naive Bayes. And then if you're familiar with Gaussian naive Bayes, there's another of those statistical models. There are some assumptions, right? That you need independence, you need, normality and all of that. But again, keep in mind that here, when it comes to Kaggle and these type of competitions, what it matters at the end of the day is, improving your score. So if you are building a model, right, and maybe one of two of the assumptions behind the model are not met, but the overall performance of the overall out of sample performance of the model improve, it still is a valid solution. Okay, so I also tried Gaussian naive Bayes, but again, I didn't notice that consistency between the local CB score and the public leaderboard score. So then I stick to linear discriminant analysis as my final estimator or as my meta learner. And then basically what I did is I built a bunch of different stackers, and I think it was some number on the 50, around 50 or 60 different stackers that I built. And then I focused on my top 4 stackers, and then I used those 4 stackers, and then I combined them using a technique that is called hill climbing. Okay, so hill climbing is a technique in machine learning that basically is like a weighted average ensemble. Okay. However, the technique goes as follows, right? So then first, out of all the models that you're planning to combine, right, via hill climbing, so first you need to identify which of those models is the best one. And that is your starting point. And then after that, you're going to identify the second best, then the third best, and so on. Okay? So the algorithm is pretty simple. Is what I call is a brute and force approach. And the reason why I call it a brute and force approach is because once you identify the best model that you have, right, and then you identify the second best, basically is you're going to try a bunch of different weights, right? So you need to define some sort of like a range of weights that you want to consider for the second model, and you will go into a for loop to identify the best way, if there is one, to multiply that second model by that way, so that by adding that to the best model, the overall performance improves. If there is such a weight, so then you just combine those two models in that fashion. If there is no such a weight that will help to improve the overall performance of the framework, then you move on to the next best model, and then you keep going through all the models in that fashion. So that's what is called is hill climbing. So then you start with your best model, and little by little you start climbing the hill. And in terms of optimization, right? If you get to the top of the hill, is that you find the optimal solution, right? So then with these 4 stackers, so then basically I use the out of fall predictions from those 4 stackers, and then I combine them using hill climbing. Okay, and that was my best solution. Okay, and that is the solution that I think is here. Where is it? The solution that this one right here. That was my base solution. Hill out of fall submission 3. Okay, and then what it worked on this particular competition, what worked was treating all the features as categoricals, and then adding multiple copies of the original set to the data set for training purposes. So those were the 2 tricks that were identified on different discussions in this competition that helped to improve model performance. What didn't work was feature engineering. I tried a few different ideas, or a few different standard ideas when it comes to feature engineering, but then it wasn't helping with model performance. On the other hand, it was hurting the performance of the model. So then now let's go back here to my code. So then we can start with Cat Boost. So then, as you can see, I built a bunch of different models, a bunch of different Cat Boost experiments. So for any time that I will find, a good, in some sense, out of sample performance, I will save those predictions. So let me show you one of those. Boom, boom, boom. Yeah, so for example on this one, right, so then this is the very first prediction that I start saving. So then this is the configuration that I use. And in this case, yeah, I didn't use any feature engineering at all. It's just raw data. This is the cat boost hyperparameter configuration. Run the cross validation strategy. Here is the auto sample performance for each of the folds. So here is the overall performance of the model, and then I save the auto sample prediction and the predictions on the test data set. Same thing for LightGBM. I build a bunch of different models. You know, anytime that I will find a good model, I will save the auto fold predictions. Same thing for XGBoost. I build a bunch of different XGBoost models. Logistic. So I also build a logistic regression model. But one thing that I want to make sure that I mention is when it comes to the logistic regression, there is this great discussion pause that I think most of the Kagglers benefit from it. So it's a discussion by Broccoli Beef. I don't know who that is, but then he's one of those Kagglers that like to share a lot of insightful discussions posts. So then here in this post, he pretty much focuses on building a very competitive logistic regression model. So I steal some of the ideas that he proposed here. So then basically the main thing that he's proposing here is, number one is treating all the features as categorical regardless if they are numbers. Number two is create two-way interactions, and number three also create three-way interactions. So I use those ideas to build a very competitive logistic regression models. Okay, and in fact, so logistic in this particular competition happened to be my second best model. My best model was XGBoost, followed by logistic regression, and then after that, LightGBM. I also, you know, stealing those ideas from treating everything as categoricals, creating two-way and three-way interactions. I was also able to build some competitive multinomial naive Bayes models, so with very decent or very competitive scores. So cat boost in this particular competition didn't perform that well, but still I built many different cat boost models. I also built a few different his gradient boosting models, but again, I didn't find a very competitive his gradient boosting. His gradient boosting was one of those models that it was taking a long time to train. I also, what is it? The gradient boosting learner. Let me find that notebook is here. So yes, I also play with the gradient boosting learner algorithm. So this by far was the slower one. So then just to run one experiment, it was taking a long time. Okay, so my first experiment took 2 hours, you know, given the size of the data. And one of the drawbacks of this algorithm is a great algorithm. I really like it a lot because there is no much hyperparameter tuning that you need to do. However, it doesn't leverage GPU computing yet. So I hope that in the near future, you know, or on the next version of the library, they include GPU computing. Because yeah, look at this. When I ran another experiment, it took pretty much 7 hours to run. And again, it's because of the size of the data, 750,000 rows, and then you're running this experiment over 10 folds, so it takes some time. Okay, yeah. So then I try all of those try a bunch of different models. Again, especially on these type of competitions, the more models you try, the better, because again, you can see what is working and what is not working. And then here I have my stackers. So the one that my best stacker, I think it was stacker 36. Let me get to that one. Where am I? Well, 24, 30. Come on, almost there. Yeah, so then this was my best stacker. So it was a combination of 6 models. So then CAD boost, XGBoost, light GBM, his gradient boosting logistic, and multinomial naive Bayes. So I used the out of fault predictions from those 6 algorithms as inputs into a stacker, and the final estimator was the linear discriminant analysis. So that was my best stacker. And then I use another 3 stackers that eventually I use it for hill climbing purposes. Okay, so yeah, just to give you an idea of, visually speaking, of what I was doing there. So this is my best solution right here. So in this case, let me move this a little bit. So what I ended up doing is, so I have 6 different models, or I have a bunch of different models, right? So then, for example, you have model 1 here, model 1. So then here you have model 2, and so on. So let's say, I don't know, for illustration purposes, let's say it's model 10. So then I build, for example, with some of them, I build one stacker here. So stacker, we can call this stacker 1. And then with another of those, I build another stacker. So let's say stacker 2. So in my case, I ended up with 4 stackers. So stacker number 4. And then I use those 4 stacker out of fault predictions in hill climbing. Okay, so that's something that is very important, especially when it comes to combining models. You need to make sure that there is no data leakage, and make sure that you are using out of sample predictions to combine those models. Okay, otherwise you're going to end up overfitting the data. Okay, so then I use the out of fault prediction of those 4 stackers, and then I run my hill climbing algorithm again. So then here is the individual performance of each of those stackers, and then basically that's where the brute approach kicks in, right? Identify the best one. So then in this case, the best stacker is stacker number 1. That's the one that has the higher map at 3 score, and then it goes to the second best, which in this case is the second stacker, and identifies that by multiplying the second model prediction or the second stacker prediction by this weight, so we boost the out of sample performance, and this is a new out of sample performance. Notice that initially is 0.31863, and then here we have 0.31864. So there was a very, very minor improvement. Realistically speaking, so that minor improvement is not going to matter that much. But again, keep in mind that here in Kaggle, the 0.0001 difference matters. Okay, so then here, this is the weight, the hill climb being found for model 2, and this is the weight that it found for model 4. For model 3, it didn't it didn't found a weight that it will help to improve the overall performance. So it didn't include Model 3 at all in the ensemble. Okay. So yeah, so then that was my solution that I wanted to share again. So then feel free to go to the site here, and you can read the first solution by Chris. Chris is a living legend in Kaggle, so then he always shared a lot of knowledge. And then here you can also see the other write-ups for the different solutions. So then, yeah, so as I always say, Kaggle to me is the best platform to not only to learn new techniques and to learn new tricks, but also to stay up to date. With either traditional machine learning techniques, AI, and other techniques that may be developed in the future. All right, so that's all I have, and see you on the next one. Thank you.